Hi everyone, welcome to another edition of the OnTrack Whiteboard video series. My name's Ben Jordan and today I want to discuss the topic of castellated modules or castellation, or castellated as most people call it. Castellated modules, what are they? They are, or castellations let's say, is when you have a partially edge-plated connection on the edge of a printed circuit board. And they are becoming more and more popular again. They've been around for a very long time, since the 70s, probably even earlier, as a method of packaging multi-chip modules and hybrid electronics into small modules that can be directly soldered onto the carrier board. And so this is kind of part of the series on multi-board design, and I thought it was important to bring this up because castellations have actually become very popular again for many of the different boards now available or being designed for IoT and sensor nodes and mesh networking. There's a lot of very small modular products now hitting the market, which more and more are using castellations as a method of connection. And so I thought it would be important to discuss some of the issues around that. So let's start with how these are made. I think the most important thing to be able to do anything right in PCB design is first understand how is this thing actually going to be fabricated. So in the factory, not every PCB fabricator likes doing castellations because there are certain issues around manufacturing them. Most of them can do it and will if you talk to them and explain to them what you're trying to achieve. Excuse me. So let's quickly talk about it. Castellations are made by designing pads that encroach on the edge of a PCB. So in this diagram here, I've got a theoretical edge of a printed circuit board design, and in the actual CAD tool, you've got your board outline defined as a straight up line, and the castellations is simply placing plated through hole pads or vias on the edge such that the plated through hole encroaches upon the routed edge of the board. And you could say, well, that's how you design castellated modules. Super simple, right? Not so fast. First of all, you have to communicate your design intent very clearly to the manufacturer. And so something needs to be done even at the PCB design level to indicate this is what you're doing. Many designers talk to their board fab, which is always a good idea. Always talk to them first and say, how do you want this data? What they'll probably tell you, most of them would say this, is to use a mechanical layer in the CAD software, in the PCB editor, draw a line that represents the routed board edge. And in your manufacturing documentation, in Altium Designer, we would use Draftsman for this, or some people would use mechanical layers. But you need to put a call out to say this is a routed edge, right? You need to note that these are castellations with a call out so that the manufacturer can look at that and know. Now, of course, the actual manufacturing outputs, the NC drill files, or the ODB++ or IPC 2581 or Gerber X2, take your pick, will have the information for routing the board in it. So this routed edge is actually going to be in the NC file, and normally you can create a separate file for, and this is what you should do, pre and post routed and drilled holes. So what does that mean, pre and post? Pre-routed means you're going to plate through. So a hole goes through the board, it's drilled before plating. So it's a pre-plated drill. And every through hole, in our case in Altium Designer or other Altium CAD tools, whenever you generate an NC drill file output, you have an option of checking a box to say create separate files for plated and non-plated holes. And this allows the manufacturer to place all the drill hits that need to be plated through before the plating bath, because they're all in one drill file, and then all of your board edge routing, which is typically after all of the fabrication, is done later. So that's in a separate file. That's in the unplated. And so in plated, you start with an actual board. Let's just draw here. You start with an actual board, and you've created holes that are plated through. So on the manufacturer's fabrication panel, that board edge is not done at first. So what they are going to have to do, and you can work with them to either provide this for them or let them do it for you, which is probably a better idea. You define your board edge, but you're going to place some mouse bites on the corner according to IPC 2222B. There's some guides on how to do this. So you place your mouse bites for breakaways, but then you're going to have a route tool path with a suitably large tool diameter that crosses the edge of the board. And this will cut through those plated through holes that have already been there done as a prior step in the manufacturing process. But this creates mess. When you typically route through plated through holes, you might have this kind of thing. It might look like this on the edge of the board. Let's just do something like this. But you've got plating copper that's going to be hanging off of the edges of that, like swarf. So you need to specify how clean you want this, and maybe talk to the manufacturer about what kinds of cleaning processes they offer. They may have a mechanical brush that is like brushing a steel wire brush to wipe that stuff away. They may require, like some prototype manufacturers I've seen, they've got blogs on how they do castellations, and they say cleanup of the board edge is up to you. You may need to manually add an extra step to your assembly process where you rub it on some abrasive. So you must think about this and plan ahead. It's going to add time and cost to your manufacturing. Okay, so that's basically how they're made. Now, this type of castellation I call concave, and it's the most frequently used in PCB design. There is another kind which is convex, and it's used more with ceramics and packaging of hybrid electronic devices like resistor packs and things like that. This is simply where you start with the substrate, and you have your electronic devices on it, soldered on as part of another assembly step, or maybe they're printed. They might be thick film printed resistive compounds. And you have plated edges, that's copper, and probably gold or silver plated copper or tin. And then the routing tool comes in from the sides and cuts into, let's say this is a route tool path, and it cuts into the sides of your substrate like this. Right, so that ends up, on the other side I'll draw what it would look like. You end up with these. And these cuts isolate electrically the edge plating on the main substrate, and thus give you connections in between them. And there are people pioneering this method to get very high density through hole, good signal integrity connections as well, where you might have inside a PCB, you might have a routed slot that has notches in it, and there are traces with edge plating, so it can change layers through the PCB. And I forget the name of this process. It's been patented, but this is just a variation. It's like an internal variation of the convex multi-board or castellation. Okay, so what are some of the other considerations? Because, let's talk about rules real quick. Because you're placing holes on a board edge, naturally the CAD tool wants to say that's a violation of design rules, so you're going to need to make a pad class for the actual connections around the board edge. And also you want to have a very specific alignment or orientation and alignment and orientation of your connections. And so the best approach we've found for doing that is to create an actual component or a footprint in a library that represents the board edge connections. And those have predefined positioning. You decide your number of pins you need, or connections. They're not pins technically, but they're lands that get soldered to. And you need to decide what's the orientation of them, and how many there are, and what is the actual spacing. And from that you can develop a data sheet for your module where you define the mechanical outline and all of those necessary things for using the module that you've designed. But that gives you the benefit of having a footprint that you can very easily modify to become the host board land pattern, where instead of having through holes you have surface mount pads that solder to the castellated terminations. So we'll come to that in a sec. But because you're placing drill holes on a board edge, the PCB editor needs to know that's not a violation of design rules. So you want to add them all to a pad class, create a design rule that says the clearance of these holes to the board edge is allowed to be overlapping. They're allowed to have zero clearance. Okay, so let's talk about real quick some assembly or usage considerations. What you're doing is you're taking an existing assembled, soldered, presumably tested and functioning circuit board and putting it directly over another and reflowing it again. And so there's a few things that we need to think about with regards to solder paste, temperatures, etc. It's very important to characterize your castellated module for the parts that are on it and what their solder reflow profiles are, and read the data sheet of your design, of every part in your design, find the information you need for their reflow profiles and how many times the semiconductor manufacturer says it can be reflowed, because obviously it's going to go through the machine maybe several times through the reflow oven. Those parts are soldered to the module's soldered to another module, so it's going to go through a few times. And so that being said, you want to make sure you're not cooking those components too much. And in addition to that, note that all those parts on your castellated module, which is on the motherboard, are in effect a heat shield to the base board that they're getting soldered to. So just know the solder reflow might take longer once it's in its final assembly stage. So you need to make sure, and again, check with the manufacturer data sheets for the parts on your module design to make sure it's okay. A lot of people using these castellated modules are hand soldering them or using selective soldering around the edge. If you're using selective soldering, it's much less of an issue because the heat is more localized to these actual connections. One other thing to talk about here is solder paste volume. So how do you know if you've got a really good castellated connection? How do you plan for that? Really, there's only one guide for this. That's IPC 610. So this is a pretty heavy book. This is about acceptability of any kind of printed circuit board connection. And so IPC 610, I guess this is up to revision G or so. It's been around for a while. There's one short chapter on castellated terminations, and it shows the concave multi-part resistor there, but this guide actually does have some really nice imagery to show what's acceptable for class 1, 2, and 3 PCB assemblies. And class 1, 2, and 3 basically means consumer, high reliability or ultra high reliability, like aerospace and medical, etc., or automotive. And it talks about pad alignment and solder paste. What's an acceptable solder paste fillet? It can go all the way up to the top of the pad, but it shouldn't go over the top of the component. And as a minimum for class 1, you should at least have a visible wetted joint. So how do you work out what's needed? Because in this case, you can see, and this is the case with many castellated modules that are on the market today. They not only have the castellated edge plated connection, they also have a through hole in case you wanted to attach it with 0.1 inch pitch headers, for example. You can attach it by soldering through pins, and that's kind of useful in a prototyping context. But if you're intending this to go to mass production, if you design your castellated modules to have an additional hole there, you've got all that volume that could wick away the solder paste. So how do you work out what's going to be needed for this mounting on a base board? You need to do a little bit of calculation. So down here, let's see, if we have a through hole via, that's a cylinder, and we have next to that our edge plated meniscus, and that goes to top and bottom pads, right? And so this is a cylinder. What's the volume of a cylinder? Here's the H. So using this as an example, let's say our board is 1.6 millimeters thick, which is pretty common. And then we have this cylinder. Let's say that's a 0.8 millimeter hole, plated hole. So our radius is 0.4. So it's pi r squared h is the volume of that cylinder, and that's the potential volume that could suck all that solder paste up into it. So what's that volume? Well, I worked it out here, and it actually, for this case, we've got pi times 0.4 times 0.4, because it's the radius, not the diameter, times 1.6 in millimeters, right? So our volume in millimeters of this barrel is, it works out to approximately 0.8 millimeters cubed, right? Which doesn't sound like a lot at first, but if you consider a typical land pattern that might go directly under this castellated pad, right? We have a land on the PCB this is being mounted to, and the solder paste stencil, thickness of the stencil for the solder paste, let's say a pretty typical thickness if it was stainless steel would be 0.01778, which is, it's a 7 mil, right? Even that's pretty thick. A lot of stencils are 5 or 2 mil. I think that's right. And then we might have a 1 millimeter wide pad by 2 millimeters long, let's say. And so we have this block of solder paste, the volume of which is 2 by 1 by 0.01778. And so that volume works out to be it's really small. It's like 0.3, is that right? 0.03556 millimeters cubed of solder paste. So there's no way, I mean this thickness here I've drawn is exaggerated. There's no way that's going to fill up all that barrel. So wicking is a real issue. So what do? If you really want to have a through hole option on your castellated hole, like this, looking down on the board from the top, and that's the pad, you can keep the copper there, but make sure you put some solder mask over it to create a dam. So we have green solder mask, or whatever color you use, and you put a solder mask dam over there. So solder from your edge does not wick into that hole. Pretty simple, right? Pretty simple. Okay. Or just don't do that at all. But this gives you an idea of what's going to be required for the land pattern or footprint that your module is going to mount onto. So let me erase that there. So I have my castellated module with its castellations around the edge. Right? And that's going to get mounted onto a footprint. There's the bounding rectangle with pads. I'm not drawing this very well, but as such, and I'll throw up an image of a module we designed like this, which is in some of our reference designs. And if you don't have this hole to wick up solder, and you're okay with a small meniscus or fillet, it's called a solder paste fillet. If you're okay with a smallish fillet but a pretty reliable connection, these pads should be extending beyond the edge of the castellated module by some amount. I'd say 20% is a good rule of thumb to get a decent solder fillet. But again, consult with your assembler and the manufacturer to figure out what's the stencil thickness, what's the volume going to be, and is it going to be enough? Generally speaking, if you don't have the wicking problem, this is going to work perfectly every time. And it's the only consideration then is reflow temperatures and multiple cycles of reflow for the components which are on this board, on this module. But if you do need extra solder volume, then you can use this this trick where your solder paste stencil is going to be modified, and even though the copper pads are only this big, let's draw a copper pad here. This is your copper pad for your footprint. The castellated module is going to be mounted over it here and has the meniscus and about that much copper. So you've got enough. You may have enough solder paste, but if you want extra, you modify your paste mask stencil to extend beyond that. And yes, solder paste will be over the solder mask here, but during reflow, all of that's going to get sucked up to making a really nice solder paste fillet on the edge of your castellated edge plated hole. Okay, just one last thing. One reason a lot of castellated modules have hit the market lately is because of the IoT and because of strict FCC, CE, CTIC. It depends which country you're in the world, but there's regulations as to radio frequency interference, or EMI, electromagnetic interference, and electromagnetic pollution is a real deal. Yet we have wireless lives now, and there's so many things connected. There's little modules you can get that'll do sensors, alarm systems, where instead of running cables everywhere, you just attach a thing with a battery in it to the door and it knows if the door's open. All of that stuff connects over Bluetooth, Wi-Fi, almost everything using the 2.4 gigahertz sort of region of the spectrum. And so many modules have been developed to ease the process of getting a product certified. If we certify the module, so goes the logic, although this is not strictly true, but it's what most people believe. If you certify just that module for FCC compliance, then you can use it in any product and you're good to go, and you don't need to go through the hoops of getting things tested for compliance for EMI. That's not actually true. You still need to get your product tested and pass. However, it also means that the RF and microwave portion of the design's been done by someone who knows how to do it, and all you have to do is plug it in and use it, and send your SPI bus commands to the module or whatever. So, but that being said, I've seen a lot of mistakes done with Wi-Fi modules and Bluetooth modules, which inevitably, let me erase some of this. Right? We have a module. There's castellated connections. A classic example is the ESP series from Espressif. Let's say this is an ESP12. And then there's a metal can shielding the chips on the module, which also helps, by the way, with reflow issues and so on. And then through the edge of the can comes an inverted F antenna, like this. That's a PCB trace. That's a Wi-Fi or 2.4 gigahertz omnidirectional antenna. And that's great. They've designed everything, they've tested it, it works, it's got pretty good range, I don't have to care about it. But I've seen numerous times where this module is mounted on some bigger PCB and there's copper polygons and planes everywhere, right under that antenna. Well, you're gonna wonder why your range is terrible and why it keeps dropping out. These things are designed assuming that this module is the only dielectric under that antenna, the only substrate there, and all of that affects the impedance and the frequency response and the ability to radiate the energy and receive the energy that it needs to radiate and receive. And the moment you add to a module additional substrate of the same kind, so this, let's say that's FR4, and this is FR4, so it's even the same dielectric constant, but adding that additional thickness definitely has an effect on the impedance and the performance, the propagation performance of something like one of these PCB antennas. So just bear that in mind. These work pretty good even if you add extra FR4 under them, as long as there's no copper in it. So if you're going to do that, make sure you create a keep out area. You might have one or two power traces or something, but really the best way to do this is to have your module off the edge of the board, if you can do it, with its antenna section off the edge floating in space, or at the very least place it towards the edge of the board and make sure, there's your antenna, make sure there's no copper under it at all. No copper, no traces. Put keep outs there so you can't accidentally route there. Well, that was probably a lot longer than I was anticipating, and hopefully it's been valuable and useful to you. If you like this and other technical videos that we're doing for OnTrack Whiteboard, please comment below, let us know what you want us to cover and talk about, and we'll do our best. If you like it, please give us a thumbs up, subscribe, and share it with your colleagues and friends. I'm Ben Jordan, and thanks very much for watching. See you next time.